Okay, so this morning we're going to talk about what we call the quantum mechanical postulates. Now, the thing is, last time we talked about managing that messy mathematics, we looked at the equations that Schrodinger used to solve the hydrogen equation or the hydrogen spectrum, and we didn't really explain where those equations came from. Okay, we just sort of listed all of these different equations. Well, many of those equations were what we call postulates. And so let's look at this word. Now, you can use it as a verb. You can postulate something, and it's to assume the existence or fact or truth of something. So this would be your foundational assumptions. Okay, one of the most foundational assumptions we have as scientists is that nature is repeatable. But you can't prove that. It's an assumption. So if you see a change, two things could have happened. Either a variable changed in the system or nature changed. And you can't decide. And so we postulate that nature is stable and repeatable. So therefore, something else has changed. One of our variables has changed. Temperature's changed. Something about the system has changed. But nature itself operates in repeatable ways. But we can't prove that. So that's a postulate. So these are some of the mathematical postulates that helped Schrodinger solve the hydrogen equation or hydrogen atom spectrum. And so a noun is a postulate, a thing to assumed as true as the basis for reasoning, or you can, in mathematics, it's an assumption used as the basis for mathematical reasoning. And so these are the quantum mechanical postulates that we're going to cover today. And this is directly from Atkins. And so you can find more explanation of this in Atkins if you go to the table of contents and find the quantum mechanics part, because some people were emailing me, what chapter are we in? Okay, go to Atkins. You can use any of these topics that you see in the lecture, and you can go to the table of contents or the index, and you can find further discussion in your Atkins book. So this lecture covers those postulates that are the basis for quantum mechanics, or the math of wave mechanics. So postulate one. Now notice what we're saying here. We're saying that this is the way things are. Now, we could be wrong, but we're going to start with this. So the things that we show today are not, they're assumptions. Okay. And so these are the assumptions that allowed us to solve the quantum mechanical mathematical issues. Okay. But it's a little uncomfortable to think that all of these assumptions really themselves are not provable. We have confidence in them because they match the data really well. But there could be other math out there that matches the data better. So we gain confidence in these postulates because of what they do. They allow us to match the spectra. And like for Schrodinger, it was matching that hydrogen atom spectrum. Okay. For us, we're doing just a simple particle in a box, but we're able to generate the full Blackbody spectrum. And so it gives us confidence that we could start with these postulates and we can describe nature very well. So that's where we get our confidence in the postulates. There's nothing underneath them to support them, but downstream from them, it matches the data. But it could be a coincidence. Okay, it's a very improbable coincidence that we would be able to match the data so well. And so that's what gives us a lot of confidence in these postulates. But it's kind of interesting that you've gone through, from Gen Chem through organic and so on, and now you're at PChem, and we're actually scratching at the roots of the whole system. We're down to the foundational assumptions. And that's got to be pretty exciting, because below this is kind of a void. We don't really know what's behind these wave functions. That's where we get into philosophy. But if we start at the math of the wave functions, we can do lots of math and get lots of experimental results, and we can understand what goes into those experimental results. So postulate one is that the state of a quantum mechanical system is completely specified by the wave function. And so if we understand what a wave function is, we're talking about these standard waves. Can I get you to help me? Since you're up here in front. So this is my slinky. I'll hold that end. Okay, and you just hold yours steady. Okay, let's scoot back a little bit because it's a long one. Okay, and so this is the ground state. I just wanted to show you visually what we're talking about, standing waves. You see the ends don't move, just the middle moves. And you see the frequency, it's pretty low. That's the lowest frequency state. Now I can go to the n equals 1. This is n equals 1, so n equals 2, I have to double the frequency. So I'm going to start, let's see, there we go. That's it. So when we draw those images, we see the lobes and the nodes in the middle. It's not really moving. Now I was driving down between Brenham and Navasota, and one of the power lines was doing this. The wind was blowing on it, and I pulled over and like got a selfie video, like, check this out, it's n equals 2 wave function. And so I put that on Facebook, and my daughter was like, oh man. So I'll try to get n equals 3, but it gets a little more difficult to get it to be stable. So this would be a non-standing wave. Okay, there we go. So that's n equals 3. Or is it n equals 4? No, is the middle just moving? Yeah, okay, so there's 2 nodes? Okay, so that's n equals 3. Now, this is, again, higher energy. You see the kinetic energy? Much higher. And the Schrodinger equation, that Hamiltonian, that's the second derivative, look how curvy the wave function is. Second derivative is the curvature. And the second derivative is the energy. So the curvature of the wave function gives us the energy. Thanks. Let's give her a hand. So if we understand the wave function, we can understand the quantum mechanical system. Now the square of that wave function, notice some parts were positive, some parts were negative compared to just a straight line. And so if we square it, all those negative parts become positive when we integrate over all space. If we were just to integrate the first 10% of that, you've got a particle that's confined to a box, and 10% of that box should contain a 10% chance of having the particle, right? That's what Newtonian physics would tell us. That the particle, if there's no potential energy inside the box, the particle is going to roam around and, on average, be in the first 10% of that box 10% of the time. And if you do a quick integration and you integrate the first 10%, you don't get that. You get just, I mean, it's like a 3% chance in the ground state, because it's very small at the beginning of the box, and then it gets big in the middle and very small at the end. If you square that wave function, it gets even worse. And so this is the quantum effects of sort of location in the box. So the square of that wave function is going to give us that probability distribution where the particle is inside that confined space. Now, this leads to a couple of things. If that's the probability, and if we integrate over the whole box length, then we ought to have a probability of 1 of finding the particle. So if the wave function squared is the probability distribution, when you integrate that over all space, then that integral should equal 1. Because that's how probabilities work. They go from 0 to 1. And so if you integrate over everywhere, you're going to find the particle. And so that's where we end up with these long integrals to, you have the wave functions times each other. And if it's 3 dimensions, you have x, you have y, you have z, and also time. So it's really 4 dimensions. So that's a quadruple integral. And we're not going to do that, though. We're going to do this one. 1 dimension, because we're a particle in a 1-dimensional box. So all space is from the left side of the box to the right side of the box. It's not a problem. Okay. But it's pretty much the same math. It's just more tedious. So that's postulate 1. Now this leads to this requirement that the probability distribution sum to 1. That leads us to have normalization. So we have to normalize our wave functions so that when they're squared, and when they're integrated over all space, you get 1. Now we also need wave functions that are orthogonal to each other, and we'll explore what that means. So we need certain types of functions. So we need a wave function. The slinky wouldn't be very good if it was broken in the middle, and so it needs to be continuous. It wouldn't be a very good slinky if I had bent it and kinked it. So it needs to be not kinked, and so that's the continuous first derivative. So these wave functions for atoms, nuclei, and molecules have been developed, and they must have these 4 criterion. Continuous, they must have a continuous first derivative, because we're going to take the second derivative. And if you were to integrate this or differentiate this function, you could find the slope from this way. At this point, the slope is negative going down, but if you were to integrate from this side going backwards, the slope here would be positive and going up. And so if you were to plot the first derivative, it would be discontinuous. We'd have a negative. If you came from this side, it'd be negative. If you came from that side, it'd be positive. And then how are you going to take the second derivative? You can't. Okay, so we have to have a wave function that's smooth, not pointy. It must be single valued, so it can't loop back on itself, and then it can't be finite, because if I'm going to integrate over all space and I have an infinite piece in the middle, I can't divide that by anything to get it to equal 1. Okay. So these are pretty simple criterion. And a sine function, a cosine function, e to the x, which is essentially the sine and cosines added together with an imaginary number thrown in, those are all, they meet all of these. And so really, all of your wave functions can be computed using sines and cosines and e to the x, or e to the x squared, a Gaussian function. So Gaussians work, exponentials work, and sines and cosines work. So that's where, you get this huge landscape of mathematics and calculus, but in physical chemistry or quantum mechanics, we just have a subset of it. We only really need sine, cosine, and exponentials and Gaussians. Now here's the orthogonality part. Or it's really both, orthonormality. So if we integrate the wave functions over all space, they equal 1 if we're dealing with the same quantum state. If we're dealing with different quantum states, those wave functions times each other, summed together, would equal 0. And so here's a graphical picture of that. So here's the quantum numbers. So the wave function for quantum state 1, 2, 3, 4, and 5 across the top and down the columns. And this is the result of their multiplication and integration. And you see, if I have 1 times 1, I get 1. So if I take the wave function 1 times wave function 2 and integrate over all space, I get 0. Wave function 1 times 3, integrated over all space, I get 0. So this huge matrix is summed up in this thing called the Kronecker delta. When n prime equals n, then it's equal to 1. When n prime is not equal to n, then it's equal to 0. Can you see that pattern up here? In a couple of weeks in lab, you're going to do this in the spreadsheet. And this pattern is something that I want you to recognize. So down the diagonal, that's 1 times 1, 2 times 2, 3 times 3. And since the quantum numbers are the same, you get an integration of 1. And anything off the diagonal, the quantum numbers are different. And so then you get a 0 for the integration. So I don't know how you get your name on an equation. This is pretty simple, and we've got somebody's name on it. That's pretty cool. Okay, so let's look at normalization of the 1D particle in a box. So I'm just going to walk you through the calculus. I'm going to go pretty quick so that you can go back on the video. If I drag it out, you're going to get sleepy. I'm going to try to go through it quickly. You'll see, okay, here's the trig substitution. Here's some algebraic simplification. And then we get to the normalization constant for the wave function. If there was a step that you missed out on or something like that, then if it's just a quick question, go ahead and ask it. But if you want me to repeat it or whatever, go back to the video. And then if you still didn't get it, email me, okay? Or we're going to run out of time. And I'll get through this, and then we'll do the Kahoot. Okay, so we're wanting to set up this integral over all space and set it equal to 1 so that we can determine what to put in front of our sine function. So we know our wave function is probably going to be a sine or a cosine. Let's just choose sine. And we need to figure out what constant in front of that sine can cause this integration over all space to equal 1. We want to have a normalized wave function. And so we put this n in front. Let me use my pen. This is our normalization constant. We put it in our wave function. So this whole piece right here is the wave function psi. And here's another one of them. So you see psi is times psi. And each one of them has this normalization constant inside. So again, we're doing an integration with respect to x, and that n is a constant, so we can pull it out front. So we pull the n out front, and we have two sine functions. The arguments inside the sine function are the same, therefore it's sine squared, right? So you can just say if the stuff in the middle is in the parentheses is the same, then you can combine that and make sine squared. Now I know my integration of sine and cosine, but I'd have to look up sine squared, but I could also use a trigonometric substitution and get that down to cosine where I could do the integral pretty easily. So I'm going to use this trig substitution. Sine squared of u is equal to essentially 1/2 minus 1/2 cos 2u. So this is what I've done. I've done that substitution. And so I have the 1/2 here, which is this first part, minus 1/2 times the cosine of whatever was inside this business. So this right here was u, and so I have 2u. Notice this is a 1/2. When I multiply it by 2, it goes away. And then I have this piece here multiplied by 2. So that's my trig substitution. Not a problem there. And now I have an integral of a sum. And so it's really two integrals. I can integrate the first piece, and then I can integrate the second piece. So here's the two integrals. This first one's the easiest integral you'll ever do. The integral of dx, we just get x. Okay. Sometimes that trips people up because it's so easy. They're like, what is that? Well, don't overthink it. The integral of the derivative of x is x. Okay. And then this one, we have to remember I always remember the derivatives, right? And so the derivative of sine is cosine, therefore the integral of cosine is sine. Okay. And so then we've got our two integrations. So this integral here became x, and then this whole integral from cosine became sine. And then we also have to take the interior piece with respect to x and bring it out front and invert it. And so that's where this L over 2 in pi came from, but then we also have this 2. And so that gave us the 4. And then we evaluate this at L over 2, and then we subtract the same set of functions with negative L over 2 put in for x. So these pieces go in for x. And so that's this next step. So it gets pretty long, but this isn't long at all compared to the transition dipole moment. So this week's lab, you'll get to do this with your TA. So we have this first piece here. I've kind of bolded it so that you can follow along. We have L over 2 minus a negative L over 2. So this is, you can't drop that negative. We have this piece here, and then when we evaluate the two limits, we have a minus sign. And then the same thing here, although we start out with a negative function, so therefore when we take the difference, it's a positive. Okay, so we have minus sign, minus and not minus sign, so then that cancels and gives us a positive. We have L over 2 here, and a minus L over 2. So some things cancel out. This 2 cancels here, the L cancels here, and we have a minus in pi and a plus in pi. So this little piece goes to 0. This L cancels, this 2 cancels, okay. And so we have an n pi plus another n pi, so we have 2 n pi here. So we can simplify all of these things. We have the L times n squared, and we have 2 times 2 is 4. And then we have 2 negatives here, so they cancel out and give us a positive. And so we have a 4 in the denominator here. So 1/4 plus 1/4 is a half. So 2/4 equals a 50 cent. And so we have this piece right here, this n squared L over 4. And then we have this n squared L over 4. Let's see. Oh, no, that's right. I didn't make it a half yet. So we have those 2/4. And then this is the sign. This is the trick right here for this problem, is recognizing the sine function crosses 0 at every pi. So if we look at a sine function, where does it cross 0? It crosses 0 at pi, at 2 pi, at 3 pi, at 4 pi. It's always 0. You see that? And so this is 2n pi, and our quantum numbers are integers. So we have integer multiples of pi. And if it's a sine function of integer multiples of pi, it's 0. So all of the sine business cancels out. It's 0. So the only thing left are these two pieces right here. And so that gives us the n squared L over 2 equals 1. So the L goes on to the bottom of the other side, and 2 goes on the top. And so n is equal to the square root of 2 over L. So let's review why we wanted this result. This is the constant that we need to put in front of sine so that our wave function, when it's squared, will give 1 over all space. So this fixes our probability problem for our particle in a box. And we have to do this for all wave functions. I'm just showing you the particle in a box wave function, but we had to do this for the hydrogen atom. We had to do this for vibrational wave functions, for all the different kinds of wave functions in quantum mechanics. There's a normalization constant out front, and it's to fix this probability postulate. Okay. Let's pause here and do the Kahoot. So let's swap over. And it's based upon the mathematics from last time. So if you have your notes for the messy mathematics lecture, you might pull those up. What you get on the Kahoot doesn't really matter. It's just the fact that you're participating. It's an attendance grade. Okay, try to do your best, get on the leaderboard. But if you miss one, it's not too much of a problem. Yeah, so go to kahoot.it. So, yeah. It's kind of a weird suffix. Normally it's .com or something like that. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About 34 people. And if your device's battery dies or something like that, just come up and I'll get you recorded on this sheet for attendance, okay? So it's not too much of a problem. We went up, now we're losing folks. Okay. Is everybody in that wants to play? Okay. We're going to start. I think you can still join if you get knocked out. So. Okay, so in this spectrum, how many peaks do you see? Or actually, how many peaks are there, I should actually say. So, yeah, sorry. And we'll see. We'll see. It's all right. Yeah, okay, 3, yeah, so if you see here, it's like a peak, and then a kind of a shoulder. But in actuality, there are way more than 3. So I screwed you up, sorry. I need to keep my mouth shut. Okay. This equation applies to which axis of the spectrum? Do you remember this, we were talking about last time? This is the absorbance equals the Boltzmann distribution times the integral, transition dipole moment integral times the Gaussian. About good job on the 19. It's a little more than 50%. So that's the absorbance. That's the intensity part. So that's the vertical axis. All right, got some rising stars. Which piece of the intensity equation is temperature dependent? So A equals BIG. So if I say anything, it's going to be too big of a hint, so I just got to keep my mouth closed. All right, that's great. Good job. If you ever get 100%, I'll take a picture of everybody in the whole, like the screen. All right. Which one of these will calculate the emission intensity? Okay. So pay careful attention to what's in the middle. That x versus x squared. That's where that's the money right there. Okay, good. Leaning towards the correct answer. The X squared is a 2-photon process. Each X represents a photon. And so emission is a single photon just coming out of the system. The other is scattering. So the photon comes in, scatters off, they count as 2 photons. The Boltzmann distribution calculates what? So, a lot of text. Hopefully you can read it in the back. All right, it's the thermal population. Very good. Which one of these is the Schrodinger equation? It's written in a little bit different form than you've seen it, maybe. Okay, good, good. Yeah, it's this top one. You see that H times psi? Typically, H psi equals E psi, but this has been left multiplied and integrated over all space. Okay. 2 more. Which axis of the spectrum uses the transition equation? So we have 3 transition equations here. The top one's the energy transition equation, then the middle one's the frequency transition equation, and then the bottom one's the wavelength transition equation, or transition wavelength equation. Good. Okay. So there's a clue there. Typically, it's intensity versus wavelength, or intensity versus frequency. And so you see wavelength and frequency. And those would be the x-axis, or the horizontal axis. Last one. The 1D particle in a box wave functions depend upon temperature. True, false? All right, let's look at this. There's a pro tip. You see right here, I don't know if I can zoom in. No. Here's the wave function equation. You can look at the equation. If you don't see temperature, it's not temperature dependent. So, and so there you go. So let's see how we did. All right. Good job. It's somewhat anonymous. You know who you are. Friends that email you all the time know who you are. So that's cool. And I always played the Mario little cloud and the little thing at the Mario Kart. My kids are like, come on, skip this. I was like, I want to see myself on the podium. You just want to skip because you lost. All right, great. So let's look quickly at the orthogonality of the particle in the box. So here we're taking 2 wave functions that have different quantum numbers. So n and n prime. We're going to keep those. We're not going to substitute n for n prime. We're going to leave them as n and n prime. So here's our multiplication. We do have that normalization constant in there now, the square root of 2 over L. You see that? And we have n primes on the sign on the left and n's on the sign on the right. But this means that we can't combine them into sign squared. So we're going to have to do a different trig substitution. Okay. So we can pull the 2 over L out. There's 2 of them, so when they multiply by each other, we get rid of the square root. And now we have this sign of, and we can call this whole piece in the middle U, and we can call this one V. That's typically what you see in the like the cheat sheet, the substitution chart that you have in the lab. And so whenever you take that, it's equal to cosine of U minus V minus the cosine of U plus V. And so in the lab, you'll use that one. And if you have this situation, you might use, if it's sine squared, use the half angle theorem. And so now we have, again, a sum inside our integrand. And so we can break this into 2 integrals. So we can break this into two integrals. We've simplified things a little bit, collected some terms. I got all my L's over here in front of the X, and these other pieces in front of the 2. Okay. And now we can do those two integrals. And so the first one I bolded just apart from the second one so we can keep track of the algebra from here on. And so I'm going to have the L over 2 go in here for X, and then I'm going to subtract the sine function and put in the minus L over 2 in for X, and do the same thing for this one. Once we put in the L over 2, the L's cancel, we get some 2's on top and so on, and then we end up with this piece that is got a 2 in the denominator, and so it's like a half plus a half equals a whole, right? And so we end up with just this n prime times pi minus n times pi. Well, our quantum numbers are integers, and differences of integers are going to give integers. And so once again, we have integer multiples of pi inside a sign, and so that's equal to 0. And then there's also the situation when we have the minus sign here with the L over 2. Then we have this piece, which equals that piece, but there's a difference between them. And so two things that are equal, when you subtract them from each other, then it cancels out and you get 0 here. And so again, sine of 0 is 0. So our sine pieces here go to 0, and the same thing happens on this side, 0 and 0. So no matter what I have for my quantum numbers, as long as they're not the same, I get 0. So orthogonality matches with this, the way we've built our wave function. So we have wave functions that we call orthonormal. So they're orthogonal and normal. When they're multiplied by each other and it's the same quantum state, we get a normal probability, we get 1. But then if there's any wave function times any other wave function, we say there's no overlap, that 3 is independent from 2 and 5 and 50. So all the wave functions are independent from each other. We call that orthogonal. And that's the definition of orthogonal. You probably learned it when you first took geometry, that orthogonal meant 90 degrees, right? X is orthogonal to Y, which is orthogonal to Z. And we had orthogonal axes, but what that really means is independent. I can move in X without changing my Y or my Z. I can move in Z without changing my X or my Y. Well, in this case, I can be in quantum state 5 and not have anything to do with quantum state 3 or quantum state 2. So all our quantum states are orthogonal from each other. Okay, so that was all postulate 1. It was just all built into that probability distribution, and that the system can be described by the wave functions. Postulate 2 is observables. So for every measurable property, there exists a corresponding operator in quantum mechanics. So when you operate on that wave function, you can simulate an observable effect in reality. So an experiment in the laboratory to measure a value such as momentum or position or energy has a mathematical thing that is an operator associated with what's going on. If you operate on the wave function with the momentum operator, you get the momentum of the particle. And this is how we simulate. When I said all of this matches experimental results, this is how we got it to match. We found these operators that reproduce the observable effects. Now we're really just going to be dealing with the Hamiltonian operator, the one that gives us the energy. But here are the others. So we have momentum. You don't have to really write these down. They're in the lecture notes. We have the kinetic energy operator. So this kinetic energy operator here is part of the Hamiltonian, which is the total energy operator. And then the potential energy, notice it's not really specified. It depends on your system. If you have an electron around a nucleus, then you have Coulombic attraction, and that would be a potential energy operator. If you have a vibrational motion like a CH stretch, it's a harmonic oscillator, so it's a parabola. So the potential energy would be whatever function that potential energy is, whether it be the Coulombic attraction or a harmonic oscillator. There's different potential energy operators for each different setup or different system. And so that's really it for postulate 2, that we simulate experiments by using operators. And then eigenvalues. This eigenvalue equation, let me draw the Schrodinger equation again so you can kind of see what we're talking about. We have operator H, or the Hamiltonian. A lot of times to signify an operator, we put this little hat on top. H psi equals E psi. And so look at this kind of equation. This is an eigenvalue equation. Eigen meaning same. It's German for same. Okay. So notice how the wave function, you operate on the wave function and you get the same wave function back with some constants out front. And so that's how that's all of these operators that we just talked about in Postulate 2 are eigenvalue operators. They operate on the wave function and you get the wave function back with some constants out front. And so this is what we mean by an eigenvalue equation, and this right here, this energy, are the eigenvalues. So the properties of the wave function and the operator will cause the system to be quantized, meaning if you have this potential energy equation and you have the boundary conditions of which you're integrating and the properties of the waves, you're going to end up with standing waves that are quantized systems. And these eigenvalues are the quantized observables, or the energies that we have for the Schrodinger equation in particular. And so let's show the Schrodinger equation and how this eigenvalue equation works. So here's the Schrodinger equation, and a lot of times you'll see this in popular media whenever they want to show a complicated equation, in the background, you'll see this on the board. So now you'll recognize it. So we have our wave function. So we just set this up. For our particle in a box, V equals 0. So we've just used the kinetic energy piece of the Hamiltonian. It operates on our wave function and should return this constant times our wave function. So this is the Schrodinger equation for a particle in a box. But because we still have derivatives to take, it's not finished. So we're going to take the second derivative. And once we're done with all derivatives and integrations, then we're finished. Okay. This sort of ties back to back in my graduate school days. My professor for thermodynamics, he said, this course is chemistry. I'll speak English, but the written language of chemistry is mathematics. And so he just did math on the board all lecture. And he would get to a certain point and say, aha. And I would say, why are we at an aha? We've been doing math this whole time and lots of equations. Why is this one an aha? And he said two things. One, we're done with all the integrations and differentiations. And two, it's something we can go measure. So a lot of times we're going through the system and we're not to a point where we can actually put a thermometer on it or shine light on it. We can't get to a measurable result. So we'll work with the algebra and the calculus until we're finished with integrations and differentiations and we have something that's measurable. And that's when we say, aha, we're done. So at this point we have two derivatives to take. So we'll take the first derivative. So the derivative of sine is cosine. And then we pull those constants in front of x out. And so these guys came from the inside. So we have this n pi and L. They come out after we took the derivative, and sine went to cosine. And we're just going to deal with the left side of the equation because the right side doesn't have any integrals or derivatives or anything to do. And then we have a second derivative to take. And so the derivative of cosine is minus sine. So our negative sign has disappeared. So we had a minus times a minus. And so it's all canceled out and gives us a plus. And then we had another piece of this n pi and L come out. And so now it's squared. And if you look at this, this is nice. Our wave function is back. We started out with the square root of 2 over L times sine of all that stuff in the middle, and now it's back. And we're done with the second derivative. And so by inspection, once we're done with that derivative, we see psi here, we see psi there, we have energy here, and we have these constants. And so these constants are the energies. So those are the eigenvalues. And so now we just have a little bit of algebra to do. This H bar, I don't know if I've ever mentioned that this semester, but that H bar, because they used h over 2 pi so often, they just gave it its own symbol, so it's Planck's constant divided by 2 pi. And so we're going to break that up and bring out pi, and it's going to cancel this pi and so on. So this h squared over 2 pi squared, this pi here cancels this pi, and then we have 2 squared, which is 4, times that 2 is where the 8 came from. Okay, and we have the mass in the denominator, and we have L squared in the denominator, and then we have this n, which is our quantum number squared. So notice how I've separated the quantum number from everything else. These right here are the physical constants of our system. That's what we're after in science. So if we have a spectrum and we have a bunch of peaks, what do we want to do? We want to label those peaks with the quantum numbers, and we want to solve for the mass, or we want to solve for the bond length, right? The length of the system, that's telling us how big this molecule is, how big the atom is, how big the system is. This is the physical constants of nature that we're trying to get to with quantum mechanics, with spectroscopy. So I want to separate those from the quantum numbers. We label the peaks in the spectrum with the quantum numbers, and then we pull out size, and we pull out mass, and we pull out all of these things that are related to the stuff we can't see, right? You got a molecule, you can't get a ruler out and measure the bond length. You take a spectrum of it, label the quantum numbers, solve for L, and now you have the bond length. So that's cool. This is how we get into the tiniest bits of nature using spectroscopy, is with these kinds of quantized energy states. Now this tells us some things too. What does the energy of the system do as the molecule gets bigger and bigger and bigger? Okay, I hear silence. Here's the thing. When you were taking reading tests, you remember, STAR test and all that stuff, you had the paragraph and then you had questions about it. Okay, and so you'd get a question and you go to the paragraph and look for the information. That's what I want you to think about math. That's how I want you to think about math. And so you see this equation, a lot of people lock up. They've had bad experiences with math. Okay, and so one of my goals in this course is to get you over that hump, to say, okay, I got this mathematical equation here. That's just like a paragraph in a reading assignment. And you get a question and you go, okay, where is, like the temperature thing, right? Mark, we were laughing about that. Let's look at this and see if we see temperature. Let's look at this, and where's L in this equation for energy? It's in the denominator. So you go up to the paragraph, you see the energy equation, and I ask about size of the system, and you say, well, which one of these letters is related to the size of the system? It's great. It's a piece of cake. So if I can get you to look at equations as a book or as a paragraph, I have really given you a tool, a powerful tool. And so then mass. So if the atoms, if you go from sodium to rubidium, so I'm here at sodium at 22 grams per mole, and now I'm at rubidium 85. The energy is going to drop, and so size is going to get bigger, energy is going to drop, and so what that means is quantized energies are going to drop. So they're going to squeeze together. So all of them drop together. So it's like a ladder with rungs that are much closer together, because this is all of the quantized energies. Now, how does it go with quantum number? Is it linear in quantum number? Quadratic, cubic, what? It's quadratic. So that means the spacing between 1 and 2 is different than the spacing between 2 and 3. And 3 and 4, and 4 and 5. So it goes up as the square. So it goes up really quickly. The first two are close together. You have the difference between 1 and 4. And then between 4 and 9, because that's 3 squared. And between 9 and 16, because that's 4 squared. And so it really goes up quickly because it's n squared. In vibrational quantum numbers, it's linear in quantum number. So we'll see the different kinds of quantum number dependencies as we go through the course. This is the particle in a box system. So this is not the energy equation for everything. It's just for our electron on a wire. And then the last two are just real quick. Expectation values. This is where we left multiply by the wave function. We have an operator. So here's the operator, which would give us an observable times our wave function. And then we left multiply by that wave function and integrate over all space. And then this piece down here, notice if our wave functions are normalized is equal to 1. Now this is if you take many identically prepared systems and take multiple measurements, this is what the average value would be for the momentum, the location, the energy, etc. And so in spectroscopy, we take the differences in energy levels. So we have that energy equation. We would take the energy value for n equals 2 and subtract the energy value for n equals 1, and we would get the transition equation. So here are the transition equations. Let's just go through this. We've got 2 minutes. So I put in n plus delta n here into the energy equation, and I'm subtracting just the one with n. And I'm just doing the algebra. I'm pulling all of those constants out front, and then we have n squared times this other piece. The n squareds cancel. And then I go ahead and I pull one of these delta n's out front, and I end up with this energy equation. So notice I have my physical constants here. I have delta n, which is just the change in quantum number, and then I have my quantum numbers over here. So this is our energy transition equation. Now E equals h nu. So if I nu, not u. And so if I divide this by Planck's constant, so essentially I get rid of the h squared and just have h, then that's the frequency. So if I'm plotting this by frequency, this is the equation I use. And so I always pick the lower quantum state, because we went from n to n plus delta n. And so this would be the peak locations in frequency. Well, what's nu? C over lambda. Okay. So nu is equal to C over lambda. And so I could take C over nu and get my wavelengths. And so this would be the position and wavelengths for my spectrum. And we'll unpack this some more later. But with this information, you now have the ability to plot, and you'll do that in this week's lab, plot a simulated stick spectrum for a particle in a box. And then the last one is time dependence, which is there, but we really don't use it in this course. Okay.